So let me just do a brief recap. So first, what I said was we defined work done by a force. Work done by a force. The most general definition is integral f dot ds. Then there are some special cases. If force is constant, and then I told you that work done by that force is f dot s net. You take the net displacement and dot it with the force. There is also another case where if f is perpendicular to ds always at every moment, then work done by such a force is zero. Then we were discussing about a special class of forces called conservative forces. Conservative forces. So we saw following definitions. A force is conservative if work done by this force in a closed path is zero. This should be true for every closed path. So I can say work done definition is integral f dot ds, right? This is the general definition. To tell that we are doing this integral over a closed path, we put sometimes a circle on this. A circle is written. We call this as a line integral. What is line integral? In line integrals, you have a line, you have a path along which the body is moving. You divide that path into many ds displacements, ds1, ds2, ds3, ds4, like this. Okay, and for every displacement you will find the value of the force. During this displacement the force may be in that direction with certain value f1. During this displacement the force may be in some other direction with a different value. So we are doing f1 dot ds1, f2 dot ds2, f3 dot ds3, and so on, and you do this for this path. That is called a line integral. If you put a circle on the integral, it means that path is a closed path, like this. You start from here, go in that path and come back. So that's the line integral along a closed path. So if you put a circle, it's the line integral along closed path. So basically work done in closed path, if it is zero, that's a conservative force. That is conservative. Or you can also say work done by a force is path independent. Work done by a force is path independent. That is also a conservative force. I told you last time that I will prove that both these statements are interdependent. If you accept one, you can prove the other. Let's see that. Suppose there is a point A and I went to point B in one path. I call it path 1. Then I also go from A to B in a second path, which I call as path 2. Suppose I say that work done in path 1 from A to B, work done from A to B in path 1. Suppose I say it is equal to work done in A to B in path 2. Suppose I accept this. So work done in path 1 and work done in path 2 are same. From here I can prove that work done in closed path will be 0. How? I'll bring this term to the left hand side. So I have A to B path 1 f dot ds minus A to B path 2 f dot ds is 0. Now there is a rule in integral that if you have integral A to B, some integral, let us say f of x dx, you can reverse these limits and put a minus sign, minus integral b to a f of x dx. Both these are same. So if you interchange the limits, if you make upper limit lower and lower limit upper, you can put a minus sign to the integral. Because after all, if you remember our calculus lectures, if you know that integral f of x dx, if you know its value to be g of x, then integral f of x dx from a to b will be g of b minus g of a. You first put upper limit and then you put lower limit. And similarly, integral b to a f of x dx will be g of a minus g of b, which is obviously minus integral a to b fx dx, right? So you see, if I interchange the limits, if b goes to the top and a comes down, then I can put a minus sign. This is the rule. So with that being the case, here what I will do is I'll catch this, catch hold of this. Sorry, let me use my mouse. I'll catch hold of this statement. Okay, let me go to next page. Let me keep it here. Now what I can do here is I can reverse this limits. Instead of from a to b, I will write from b to a, and I must put a minus sign, but there is already a minus sign, so I'll make it plus. So you see, in the previous case, I am going from a to b in path 1, I am going from a to b in path 2, and I said both these are equal, work done in both paths is same. Now I am getting a to b path 1, so you went like that, but instead of a to b, now you have b to a in path 2, so you are coming like this. You went from a to b in path 1 and you came from b to a in path 2, and that sum is turning out to be 0. That means work done in closed path f dot ds is coming out to be 0. So if I accept path independence, if I accept this statement, from that I am able to prove that work done in closed path is 0. Both these are interdependent statements. So a force is conservative if work done by it is path independent, one statement, or the force is conservative if work done by it in closed path is 0. Or there is a third statement which we were seeing. If del cross F is 0, curl of the force is 0, it's conservative. See, we can use del in three ways. You can use del on a scalar like temperature. This is called gradient. Or you can use del with a dot product on some vector like force or velocity force. This is called divergence. If you operate del with a vector using dot product, it's called divergence. If you operate del with a cross product on some vector, it is called curl of that vector. So gradient of temperature, divergence of force, curl of force. This is how you look at it. So if curl is 0 for any vector, then particularly for forces, then it's called conservative force. So there are theorems which will prove this line integral to this curl. There are proofs, but that is beyond our scope. I am not doing that. So we saw an example last time that if the force is yzi plus zxj plus xyk, and the problem setter wants you to check whether this is a conservative force or not. So in this case, what you should do is best is to do del cross it. Let's check it. So you have on the top ijk, then you have del components dou by dou x, dou by dou y, and dou by dou z, and then you have force components yz, zx, and xy. I am writing it as a determinant, but we have to be careful. There are operators here, dou by dou x, dou by dou y. In a normal determinant, you can expand it by any row, but here you have to expand by top row. So what I do, first I take the first element, okay, the first row and first column element I, then I close the first row and first column, whatever is left I do that. So dou by dou y of xy minus dou by dou z of Zx. This is what you get, right? Then minus j into alternatively plus and minus. You close the row and column containing j. So you have dou by dou x of xy, dou by dou x of xy minus dou by dou z of yz. Then plus k into, now what you should do, close the row and column containing k, that is this. Then you have dou by dou x of zx minus dou by dou y of yz, dou by dou x of zx minus dou by dou y of yz. You have this. Okay, let me remove this. So if you simplify this, dou by dou y is a partial derivative. That means except y, any other variable that you see, you will treat it as a constant. Here x is there, that is a constant. It goes out of the derivative. So x goes out, then you are left with dou y by dou y, which is 1. So x into 1. So this term evaluates to, if I write in yellow color, x. What about this term? Z is the variable, x is a constant. So x goes out. Dou z by dou z is 1. So this also evaluates to x. So you get x minus x. Similarly, this evaluates to y minus y. This evaluates to z minus z. So ultimately, this is coming out to be 0. So del cross f turns out to be 0. So this force, whatever is written here, it's a conservative force. You see, it's not a constant force, it's a variable force. The moment you move to 0, 0, 0, origin force is 0. The moment you move to 1, 1, 1, force is 1i plus 1j plus 1k, and so on. So it's a variable force, but still it's a conservative force. Now, I want to tell you some golden rules. First, a constant force is always conservative. A constant force is always conservative. When I say constant force, neither its magnitude nor its direction should change. That's a constant force. How to prove this, that it is conservative? There are two ways to prove. Suppose I say integral f dot ds from some point A to point B, whatever. If force is constant, I can take it out of the integral and you are left with the integral ds. When you add all little displacements, it becomes the net displacement. So you see, it doesn't depend on the path. For example, you went from A to B in a curved path, but work done, if it is a constant force acting in while the body is going on this path, work done by that force is F dot S net. S net is this blue colored fellow. Even if you were to go in this path, S net will be blue colored fellow only. So you see, it is coming out to be path independent. So a constant force is always conservative. Very important idea. Constant force is always conservative. There is another way to prove it also. Constant force means you can write F as F1i. This is a constant, it's not changing. Plus F2j plus F3k. Here F1, F2, F3 are constants. You can check for del cross F, right? So it will be I, j, k, dou by dou x, dou by dou y, dou by dou z. And then you have constants F1, F2, F3. So when you expand this, for example, I into dou by dou y of a constant, it will be 0. Derivative of a constant minus dou by dou z of a constant will be 0. So you are getting everywhere when you differentiate, you are getting zeros. So this will evaluate to 0. So because del cross f is 0, this force should be conservative. So constant force is always conservative. If you look back, our gravitational force mg, at least on Earth, in a very small location, it is always having a fixed magnitude and direction. Of course, I am not going very large distances. For example, if you go from here to here, then mg, the gravitational force is not conservative. I mean, it's conservative, but it's not constant force. Why is it not constant? Here the direction was like this, and here the direction is like this. And g also can change from place to place. That is also there due to rotation of Earth and so on. We will explore it in gravitation. So if you walk such big distances, then it's not a constant force. But in our room, wherever we are stationed, if I go from one room in my house to another room, I don't think mg will change. Its direction is more or less same, magnitude also is more or less same. So I can consider, at least for now, gravitational force to be a constant force. Actually it is not, but surprising, gravitational force, whether it is constant or otherwise, is conservative. Gravitational force is conservative. How to prove that in a general way? When we go to gravitation topic, there we can write an expression for the force between two point masses m1 and m2 separated by distance r. If you take this as origin, then this arc you can write as x comma y comma z, and you can write the force in vector form and then check for conservativeness. So I'm not going to do that, but my main aim here is to tell you that all constant forces are conservative, point number one. All constant forces are conservative, point number one. Then gravity, we assume it to be conservative, we'll prove it later, point number two. Spring force is also conservative, point number three. I'll talk about it in a minute. Why spring force is conservative? Because there is a rule which I'll tell you in a minute. Okay. uh, and electrostatic forces, force of attraction or repulsion between two charges, that's also conservative. So let me write here, a constant force is conservative. Then we have gravitational force, I'll prove it later, but this is conservative. And similar to gravitational force is electrostatic force between two charges, that's also conservative. Spring force is conservative. Now spring force comes under a very special class called one dimensional position dependent force. Actually, a one-dimensional position-dependent force is always conservative. What is one-dimensional position-dependent force? One-dimensional means it should be pointing only in one direction, x direction or y direction, and it should also depend on only one coordinate. So if it points in x direction, it should depend on x coordinate. This is a one-dimensional force. If it points in y direction and depends on y coordinate, that's also one dimensional. So such forces are conservative. Spring force comes into them. It is like F equal to minus kxi, something like this. It depends on the expansion in the spring and the force is in the x direction. So it comes under one dimensional position dependent force. How do you know that these are conservative? Well, use del cross F. If I use del cross F, for example, if I take this force as f of xi, one dimensional position dependent force, then I have ijk dou by dou x, dou by dou y, and dou by dou z. F of x, y is 0, z is 0, only I coordinate is there. Okay, f of. If you look, first close this row and column, 0 minus 0, it will be 0. Then close this row and column, 0 minus dou by dou z of f of x is 0. It should depend on z if you want it to be non-zero. Then third case, this is 0. Dou by dou y of f of x is also 0. So del cross f turns out to be 0. So this one-dimensional position dependent force, this is conservative. Spring force comes under this case only. Spring force, the spring exerts force along its length, either in expansion or compression, and that force depends on x coordinate, f equal to kx in magnitude. Right? So spring force is conservative. So for our purpose, any constant force is conservative, gravitational force is conservative, electrostatic force is conservative, spring force is conservative. If some force like this is given, we have checked it here now, yzi, zxj, you can check del cross f and see if it is 0 or not. If it is 0, that will be conservative. So this is as far as conservative forces is concerned. Why this study is important for us? Why conservative force study is important? Because later we shall discuss potential energy, or rather change in potential energy, and the conditions for defining change in potential energy are very strict. Okay, we will see it later. Potential energy can be defined for two or more particles. Then the forces between the particles should be conservative. Okay, there must be no non-conservative forces. Then we can define potential energy of a system. So we will see that later. So for that reason, this is important. Now, let us come to work done by spring force. Let us see this for a minute before I take up work energy theorem. Suppose I have a spring. It is connected to a block. Spring, if it is in natural length, it will not exert any force. Spring, if it is in natural length, it doesn't exert force on the object connected to it, or it even doesn't exert force on the wall. But if the spring is expanded, suppose the spring goes to L naught plus X, then it is exerting a force on this block in this direction. Or if it is compressed, L naught minus X, it is pushing the block, exerting a force in that direction. This force is given by Kx. Whatever is the expansion or compression, the force depends on that, and K is called spring constant. K is called spring constant. It depends on the type of the spring. If it is a very stiff spring, K will be more. I think did we discuss this? Spring constant into length of the spring is constant. This comes from molecular property of spring. There is a very important idea that spring constant into length of the spring is constant. So if I take a spring of spring constant K and length L naught, suppose I cut it into two springs where each spring has length L naught by 2. Then what happens to the spring constant or force constant? It will become 2K, because spring constant, the length of the spring should be constant. So if you cut the spring and reduce the length, suppose you halved the length, spring constant doubles. Suppose you made the length 1/3, spring constant becomes 3K. So you can understand that if there is a big spring, it will be very loose and not very stiff. But if you cut it, become a stronger spring. The more the spring constant, the more stronger the spring is. Anyway, now spring force is a variable force, right? Because the more the spring expands, the more is this force. It's a variable force. So how will you find work done by such force? For example, suppose the spring was connected to a block, it was in natural length. Later somebody pulled the block, and as a result the spring got expanded to a new length, say L naught plus X naught. In this process, what is the work done by the spring force on the block? So find work done by spring force on block. I also want to find work done by spring force on the wall. Work done by spring force on wall. Let's see both. See, spring is exerting a force on the wall also. But is there any displacement of this point where it is exerting force? Because to calculate work done, we must use integral f dot ds, where ds is displacement of that point where force is applied. Here force is being applied on this point of the wall, but it is not moving. So spring never does work on the wall. So work done by spring force on wall is 0. Because only when wall is displaced, spring will do work. But wall is rigid, it is not displaced. It is there. Whereas the block is moving, so spring force does work. Now how to do it? Every moment spring force was changing from here to here. As the spring is expanding, spring force is changing. So we'll take some intermediate position when the spring expanded by x. So then the force on the block is kx to the left. Suppose if the block further goes to the right by dx, because block is going to the right, spring is expanding, work done will be force into displacement into cos of angle between them, cos 180. Why 180? Because spring force is to the left on the block, displacement of block is to the right. So cos 180 will be -1. This is the little work done for displacement dx. Total work done while it is going from 0 to x naught. Original expansion was 0, it was natural length. Final expansion is x naught. So total work done in that case will be -12 k x naught square. Negative. Why is it negative? Because spring force is to the left, block is going to the right. So whenever the block is going away from natural length, whenever block goes away from natural length, either in expansion or in compression, I don't care, but it is going away from natural length. Maybe it is expanding from natural length, or maybe it is getting compressed from natural length. Then work done by spring force in such a case will be negative. It will be minus half k x naught square, where x naught is the final expansion in the spring. Very important result. So when spring is going away from natural length, means either it is expanding or it is getting compressed. Even when it is getting compressed, what happens? It is getting compressed. Spring will exert a force to the right on the block, but displacement is to the left. So work done will be negative in that case also. So whenever spring is going away from natural length, the work done by spring on the block will be negative. The work done by spring on the wall will be zero. Okay. What about when the spring is coming back to natural length? Suppose there is an expanded spring. It's coming back to natural length. So the force and displacement are now in same direction. So in such case, you will get plus half k x naught square, assuming it is coming from x naught to 0. Whether it's a compressed or expanded state, it's coming to natural length. So when spring is coming back to natural length, work done by spring force on block is positive. When spring is going away from natural length, work done by spring force on block is negative. So these are very important statements. This formula is very important. So I can write work done by spring force will be plus or minus half k x naught square. Very important result. If spring is going away from natural length, minus half k x naught square. If spring is coming back to natural length, plus half k x naught square. Okay. Just now I was remembering that in Newton's laws we have not done spring based questions. Did we do them spring based? Suddenly when you cut the spring and things like that.
And also, we did do spring based questions.
We did, right?
Yes, sir.
Okay, okay, good, good. Then I am on track. Okay, so this is work done by spring force. Now with this background, we will take Newton's second law and we will cook it. We will do some cooking, or we will modify it and convert it into a very powerful theorem called work energy theorem. That's my next idea. So let's look at this. So what I am doing now, spring force, this is important, this result. But let's now go to work energy theorem. Now I am coming to the core of this chapter, work energy theorem. This alone is enough to solve majority of questions, but we will develop other theorems also. We'll introduce the concept of potential energy and everything. But as far as this chapter is concerned, if you are armed with work energy theorem, if you know work energy theorem, it's like that, it's done. The deal is over. You can do any problem with this. We'll see many questions on this. So let me take the Newton's second law, F1 plus F2, so on up to Fn. All the forces acting on a particle will cause acceleration of the particle. So it is equal to mass into acceleration of the particle. This is Newton's second law. Net force acting on a particle is the cause, and it will result in acceleration of the particle, which is the effect. So net force is mass into acceleration. This is Newton's second law. The problem with Newton's laws is they are dealing with vector quantities. Like I was telling in the last class, forces and accelerations, these are vector quantities. Dealing with vector quantities is slightly tough because there is also direction associated with them, and you can't add them like you add numbers. 1 plus 2 is 3, but in vectors 1 plus 2 may not be 3. The angle between the vectors will matter and all that. So sometimes working with vectors may be tough. So we want to modify this vector equation in a suitable way into a scalar equation, and that will work wonders for us. That's what we are going to do now. That is called work energy theorem. So there is some block or something on which there are multiple forces acting, and the block is accelerating in some direction. Now I am cooking this or converting this into work energy theorem. So what I do, I'll first dot both sides of this Newton's second law with ds. That means the block is given a small displacement ds, and I am dotting it on both sides with displacement. Then I integrate. So what am I doing? Newton's second law only. I took that. Then I dotted both sides with ds, the infinitesimal displacement vector, because the block is moving, it is getting displaced. Then I integrate. So you look at the left hand side, it is integral f1 dot ds. What is ds here? Displacement of that point where force is applied. If you apply f1 here, whole body has displacement ds. Even this point will have displacement ds. Even this point will have displacement ds. Okay. So first term will be integral f1 dot ds. Second will be integral f2 dot ds, and so on. Last will be integral fn dot ds. Right side integral ma dot ds. A you can write as dv by dt dot ds. Now first let's look at the LHS. Integral f1 dot ds. This is work done by first force. Displacement is same for the whole object because we are taking it as a point mass. So the point of application of every force has same displacement ds. Okay. So this is work done by first force. This is work done by second force, and so on. This is work done by nth force. So I can write work done by first force plus work done by second force, and so on, plus work done by nth force. Now let's focus on the right hand side. It is m dv by dt dot ds. M dv by dt dot ds. This dt, I will take it to this term. So I can write it as integral m dv dot ds divided by dt. I can write like this. If you look at ds by dt, rate of change of displacement is velocity. So it is integral m dv dot v. I can write like this. ds by dt is v, the velocity. Okay, and this I can write half. I'll take m also I can take out of the integral. It's a constant. So I write m by 2 integral 2v dot dv. I multiplied and divided by 2. Why? Because now you see, now I can write this as m by 2 integral d of v dot v. Now you might be thinking, till here it is okay, I feel. See, first you wrote net force is mass into acceleration. Let me show it here, this one. Then I dotted both sides with ds and I am integrating. Then left side you have integral f1 dot ds plus integral f2 dot ds plus 1 integral fn dot ds. This is work done by first force, work done by second force, and so on. So work done by all forces. Now right side, I'm simplifying. A dot ds, A I wrote as dv by dt, dv by dt dot ds. This dt I am taking to other term and it will become mv dot dv. This is all fine. But how you got from this blue term this yellow term? So you have a rule, product rule. D of xy is x dy plus y dx. Of course, I am not telling with respect to which variable I am differentiating. If you say by dt, okay, you do by dt. But I am writing it as differentials. Writing this way, by not telling with respect to which variable you are differentiating, we call it as differential. For example, d by dx of x square is 2x. I know that. But if I just write d of x square, it is 2x dx. I took dx to the other side. This is called writing as a differential. With respect to what variable you are differentiating, I don't know. You can by 2 by dt also, it's no problem. It becomes chain rule. Anyway, so d of xy is x dy plus y dx. We can write this even for vectors also. D of a dot b will be a dot db plus dA dot b. You can do this for cross product also. Now, if you look at this, what about d of v dot v? How can you write it? dv dot v plus v dot dv, product rule. But these two are same. So this will become m by 2 integral 2 v dot dv. 2 gets cancelled. That's exactly this step. You see? So both these steps are identical. Both the steps are identical. Once again, d of v dot v, I am using product rule. First you keep first v constant, v dot dv, plus dv dot v. So it will be 2v dot dv, which is exactly what you have. Now, I can write this as m by 2. Integral and differentiation are reverse operations. So they can kind of offset or nullify each other. Whatever remains, that must be evaluated at endpoints. What remains? V square remains. If you substitute endpoints, v square minus u square, final velocity square minus initial velocity square, which is half mv square minus half mu square. Half mv square is final kinetic energy, half mu square is initial kinetic energy. So kinetic energy is defined as half mv square. That's the definition. So I'm bringing out a new definition here. Kinetic energy of particle of mass m going with velocity v is defined as half m v dot v, but v dot v is v square, so you can write half m v square. This is the definition of kinetic energy. Okay, so here if you go back, you have half mv square, that is final kinetic energy, half mu square initial kinetic energy. So what did I prove ultimately? Work done by all forces is change in kinetic energy. This is called work energy theorem. So I'll write here, work energy theorem states work done by all forces is equal to change in kinetic energy. Very natural, right? Suppose if 10 people come and they are pushing some table, what will happen? The table starts moving, its kinetic energy will change if they are doing work. If nobody is doing work, the table will remain there only. But if they are pushing it, they are doing work, whatever work is done by these persons is changing the kinetic energy of the table. So work done by all forces on a particle is equal to change in kinetic energy of particle. This is Newton's second law only, but in a scalar form. I can say this is Newton's second law in a scalar form. Newton's second law, net force is mass into acceleration. It involves vectors. Work done by all forces is change in kinetic energy. Final kinetic energy minus initial kinetic energy. This is also Newton's second law, but a modified form. Both can be sometimes you can do in multiple methods. You can do in force method also, you'll get same answer. You can do in work energy methods and you get same answer. So both ways you get same answer. We'll see examples. So my proof is done now. Work done by all forces is change in kinetic energy. This is work energy theorem. F equal to ma only has been modified to give this. The advantage is F equal to ma involves vectors, force, acceleration and so on, and dealing with them is sometimes tough. Whereas work energy theorem is all scalars. Work done by a force is a scalar because the definition integral F dot ds dot product is a scalar. Similarly, kinetic energy is a scalar. It is defined as half mv square. Okay, for a particle. So work done by all forces is change in kinetic energy is work energy theorem. Now hold up. Newton's second law was applicable only in inertial frames. If you wanted to apply Newton's second law in non-inertial frame, you must, along with all the real forces, you must also apply a pseudo force. Then you can apply F equal to ma. Similarly, work energy theorem has been derived from Newton's laws. Work energy theorem is valid only in inertial frame. If you want to apply work energy theorem in non-inertial frame, along with these real forces work done, you must also include work done by pseudo force and then equate it to change in kinetic energy. So I will write this point here. Work energy theorem holds only in inertial frames in the way we have given it. If you want to apply it in non-inertial frame, if you want to apply it in non-inertial frame, then include work done by pseudo force also before you apply it. Along with all the real forces, include work done by pseudo force also. Add it to the work done by other forces, real forces. Then you can equate it to change in kinetic energy in that frame, non-inertial frame. There are some one or two interesting questions on this. We will look at them down the line. So Work energy theorem is modified form of Newton's second law. The advantage is it deals with scalars like work done by a force and kinetic energy. So sometimes things can become simpler here. Now let us see some questions. Our first example. Now we have a series of examples. Our first example, suppose I have a 2 kg block. The coefficient of static and kinetic frictions here are 0.5. Okay. And I am applying a 20 Newton force on this. And this block ultimately it moved by 10 meters. By the time it comes here, what is the speed of this block? This is what I have to find. Okay. Now, obviously, this problem can be done with Newton's laws without work energy ideas. Let's do it first. Then I'll show you work energy method also. In this problem, though, you might feel that both are equally simple or both are equally tough. But actually, when you take more questions, which I will do now later, work energy methods are simpler. They give energy, they give the result faster. Newton's laws methods are sometimes cumbersome, very long. Anyway, let's do it here. I am applying 20 Newton force. Will the block move in the first place? Let's check the limiting friction here. Mu n, mu sn. Mu s is 0.5, n here is 20. 0.5 into 20 is 10 Newton is the bond breaking force, and I am applying 20, so bonds break. So bonds break, the block starts moving, there will be kinetic friction. Kinetic friction coefficient also is given to be same. So kinetic friction will be 10 Newton. And of course, there is normal contact force and mg. These are the forces. Since the block is accelerating only in horizontal direction, the acceleration of the block is net force horizontally by mass. That is 5 meter per second square. Now, initial velocity of block is 0, acceleration is 5, displacement is 10, final velocity I want. I can use v square minus u square is 2as. So let me use that. V square minus u here is 0, u square is 2, actually a dot s. In this case, the a and s are in same direction. So 2as you can write. 2 into 5 into 10. So it will be 2 into 5 into 10, right? 2as. That will be 10 square. So you are getting speed as 10 meters per second nicely. You got it with Newton's laws. Now I can also solve this problem using work energy theorem. How I solve it? Work done by your applied force of 20 Newton plus work done by the friction, which is kinetic, plus work done by mg plus work done by normal. Work done by every force acting on the block I am taking into account will be change in kinetic energy. Ke final minus Ke initial. Okay. Initially block was at rest, so Ke initial is 0. Now work done by normal force is 0. Why? Normal force is acting up, whereas displacement of block is horizontal. Both are perpendicular. So work done by normal is 0. Work done by mg is also 0 for the same reason. So we are left with work done by 20 Newton force. Okay, the block went by 10 meters, so work done by 20 Newton force is 20 into 10. F dot S I am using, in this case Fs, because it's a constant force. Work done by friction, friction is also constant, 10 Newton to the left. Friction is acting to the left, displacement is to the right. So what is work done by friction? F dot S will be Fs cos 180 minus Fs. So minus 10 into 10. Will be change in kinetic energy. Final kinetic energy is half mv square. What is the mass? 2 kg. Half 2 into v final square. V initial was 0. So these two get cut. From here what you are getting? V square is 100. So V is 10. Same answer you got. You just wrote one, you drew free body diagram. Then you wrote one statement like this. Work done by all forces is change in kinetic energy. Then you are finding work done by every force. 20 Newton is a constant force. So you can use F dot S, in this case Fs. Friction, it's a constant force. F dot S, in this case minus Fs, because angle between friction and displacement is 180. Then mg and normal don't do work because they are acting perpendicular to displacement. And also initial kinetic energy is 0 because block is starting from rest. So you can apply it and get V. So right now it appears that, sir, Newton's laws and work energy are both are equally lengthy or equally simple. No, we will see more questions soon where work energy will be much better. Suppose, let's do another question. Suppose I have an inclined plane, okay, and let us say the angle of inclination is theta, and I am releasing a block here from height h. Half of this inclined is smooth. This section is smooth. Half of the inclined. The remaining half is rough. So half smooth incline, no friction, and half rough. The top portion is smooth, top portion. So the block will start accelerating down nicely, no friction. But once it reaches the rough part, if the friction is too high, it can even retard. Now the block is released from height h, mass m, and it is given that block exactly comes to rest here at the end. So half distance on smooth face and exactly the same half distance on rough face, and by the time it comes down it stops automatically, okay, because it was maybe retarding in the rough section, so it stopped. Find mu for the rough section. That is the question. Let's do it with Newton's laws and see how tough it is. If you are trying to do with Newton's laws, the acceleration is not same throughout, because the smooth portion there is no friction, so acceleration is more. In the rough portion suddenly friction came into picture, so acceleration is different. So you have to consider the smooth surface as a separate problem and rough as a separate problem. If you draw free body diagram, in the smooth surface the acceleration will be g sine theta, n mg cos theta, mg sin theta, you write all those forces, it will be g sine theta acceleration. In the rough part it will be g sine theta minus mu g cos theta. How are you getting these accelerations? By drawing free body diagram and applying F equal to ma. So it started from rest. By the time it came to the boundary of smooth plus rough, it had some speed v, it gained good speed. Then it entered rough section and it slowed down and again it stopped. Finally, final speed is 0. For the smooth part, okay, by the way, what is the length of the incline? H by sine theta is length of incline. See, sine theta is opposite. Sine theta is opposite by hypotenuse. H by length of incline is sine theta. So length of incline will be h by sine theta. Now in this h by sine theta, h by 2 sine theta is smooth and h by 2 sine theta is rough. So first h by 2 sine theta smooth, u is 0. Let's get the v at the, by the time it reaches the boundary of smooth and rough. Acceleration is g sine theta. Displacement is h by 2 sine theta. So I am getting v for the smooth, v by the time it reaches the end of smooth surface. So v square minus u square is 2as. V square minus u square is 0 is 2 times a is g sine theta, s is h by 2 sine theta. So it will be gh. So the speed by the time it reaches the boundary is, by the time it reaches boundary, its speed is root gh. From there it starts retarding and comes to 0. Okay, again I'll apply v square minus u square is 2as. V square minus u square is 2. What is a now? G sine theta minus mu g cos theta. Friction is also there, because of which the acceleration will be like this. Into s will be h by 2 sine theta again. So from here, minus gh is gh, 2 got cancelled, into sine theta minus mu cos theta by sine theta. Gh will cancel. So minus sine theta is sine theta minus mu cos theta. So mu cos theta is 2 sine theta, which implies mu is 2 tan theta. You got mu. The question is, find mu for rough section. We found it. So much work you had to do in Newton's laws. Why you had to do so much work? The smooth section acceleration is different. Rough section acceleration is different. So in the smooth section, by the time it came to boundary, first find v. That will be u for rough section. and final velocity in rough section is 0. All that you have done. See the power of work energy theorem now. One step. I am applying work energy theorem for the whole motion. Work done by N plus work done by mg plus work done by friction, no other force. Is changing kinetic energy. N never does work. Work done by mg, it's a conservative force. You can go in any path. Instead of going in this path, go like this and like this. In this it is mgh, here it is 0. Why here it is 0? Because horizontal displacement, vertical force mg. It's a conservative force. So work done by mg will be mgh. Friction does work only in the second half. What is frictional force? Mu mg cos theta, that is force. What is displacement? H by 2 sin theta. Angle between them is 180, so minus. So work done by mg, work done by friction is change in kinetic energy. Final kinetic energy 0, initial also 0, because it is starting from rest coming to rest. So from here, mgh I can cancel. 1 is mu cos theta by 2 sin theta, or mu is 2 tan theta. See how fast work energy method is. One step almost. Force method you had to struggle. Smooth section, one acceleration. Rough section, another acceleration. And then you have to solve for the intermediate velocity, because the final velocity for smooth section becomes initial for rough. And final velocity for rough will be 0. So much of calculation. Work energy theorem is so elegant, so beautiful. Very fast. Absolutely fast. That's the reason work energy methods are preferred. You see, sometimes they can be very fast. I can show you our pulley example. See, suppose I gave you a pulley, our Atwood's machine, what we call as Atwood's machine. This is mass M1, this is mass M2. Pulley and strings are massless, and let's say M2 greater than M1. Suppose by the time M2 comes down by L, M1 also goes up by L. Find the speed of both blocks. Find speeds of M1 and M2 by the time they travel L. They travel a distance L. Now, how do you do with Newton's laws? You first draw free body diagram, get acceleration, then use kinematics, v square minus u square to s. Let's do that. Okay. M2 is greater than M1. So M2's free body diagram, M2G, tension, it will have acceleration A down. Pulley and string are massless. When string is massless, tension throughout the string remains same. When pulley is massless and frictionless, tension on either side will be same. Even just pulley is frictionless would do. Sometimes even just pulley is massless also, we take tension same. Okay. But in practice, it is better to be frictionless. If friction is there, sometimes tension can get affected, even though pulley is massless. Very advanced cases. So, what about M1? M1G, T, and it has acceleration A up. So, if I write Newton's laws, M2G minus T is M2A, T minus M1G is M1A. So, if you add these two, M2 minus M1 into G by M1 plus M2 will be acceleration. So, I got acceleration. For both blocks, it is same magnitude. Directions are opposite. Take any one block, starting from rest. Acceleration is m2 minus m1 by m2 plus m1 into g. Displacement is L meters. What is the final speed? Again, v square minus u square is 2as. V square minus u square is 2. A is m2 minus m1 by m2 plus m1 into g into s is L. So v will be root of 2gl into m2 minus m1 by m2 plus m1. This is the speed for both blocks, because both blocks have same speed. Their velocities are opposite, but speeds are same. Constraint demands that. If one block has speed v, other should also have speed v, otherwise string will break. Now, we had to first get acceleration, then use kinematics. In work energy, it's very beautiful. Okay. So, this is block M2, this is block M1. I will take both M1 and M2 as one system. You will be suddenly challenging me and saying, sir, how can you take both blocks as one system? In Newton's laws, you told me that their accelerations are different, so you can't take them as one system. Correct. Their acceleration for which direction and vector is different, so we are not taking as one system. But in work energy, it is speed, which is same for both. It has no direction. So I can take them as one system. So when this comes down by L, this goes up by L. Tension does zero work. Why? Here tension is doing positive work. Here tension is doing negative work. Even our virtual work method, we saw that tension does zero work, right? So work done by gravity on M2 is M2 GL. Work done by gravity on M1 minus M1 GL. Work done by tensions is zero. Will be change in kinetic energy. Half M1 plus M2 V square, because both will get same speed. Initial kinetic energy is zero. So you see one shot V is 2 M2 minus M1 into GL by M1 plus M2 under root. Work done by tensions is zero. What are the other forces other than tension on the block? Gravity. So work done by M1G will be minus M1GL, because M1G is down, displacement is up. Similarly, work done by M2G will be plus M2GL. I wrote both. Will be changing kinetic energy. Tension as a whole doesn't do work. So the same result you see, we got it here, 2GL into M2 minus M1 by M2, but you got much faster, one step. Got it much faster. So that's the advantage of work energy methods. We will see many more beautiful questions in work energy. And sometimes, Newton's laws will be very tough to get the answer, but work energy gives the answer in one shot. Something, if I have a hill like this, I release some block here, no friction, it comes down. What is the speed? Newton's laws you can't do, because every moment the slope is changing, inclined. Every moment acceleration is changing. But work energy gives the answer, tuck, in one step. Such is the beauty. So very important chapter. This chapter goes all the way into thermodynamics at a later stage, where we'll use these energy ideas. We'll go in the second year to electrostatics and magnetism. Work done by magnetic field is zero, and beautiful questions are there. So very critical chapter, very important for our 2 year course. Scoring chapter. Okay, next class I will again revise this. Any doubts you have in this? I'm actually very drowsy for some reason. I hope I did not talk anything illogical in that video. Is it okay, Amna?